In the previous video, you learned about logic gates. In today's class, we'll cover logic gates delay using binary adders. This is the elementary adder symbolic scheme. We have the two operands on 1 bit each, A and B, and we have also an input that is the carry in, the carry out, and also the value of the sum of A, B, and carry in, that is the S. Remember that computers use binary system, and so do we. This is the elementary binary adder truth table. It's easy to follow. When all three inputs A, B, and carry in are 0, the sum is 0 and the carry out is 0. If only one input is 1, S is 1 and the carry out is 0. When two inputs, like this for example, when two inputs are 1, the S is 0 and the carry out is 1. And finally, if all the three inputs are 1, both S and carry out are 1. The functions that implement the behavior after simplifying the circuit are this one. Okay, we'll learn how to do it in other day. Now we know how to sum in binary. And we can build this digital circuit that implements that function using logic gates. Okay, and now remember that we are going to study the delay that suppose the logic gates. I mean, after changing any of the inputs, A or B, the consequent change in output is not instantaneous. We can have a consequent change after, for example, imagine 3 nanoseconds. A question. If each of the gates has a delay of 3 nanoseconds, how long does it take to have the definitive value in the output S and in the output carry out? Think about it. Okay, excellent. The answer is 6 nanoseconds for the sum and 9 nanoseconds for the carry out. If each of gates has 3 nanoseconds of delay, remember, after changing A or B, you have the output after 3 nanoseconds. And you need this input that is after 3 nanoseconds to get the value S at 6 nanoseconds. Okay, exactly at the same time, you can obtain the carry out after waiting for 3 nanoseconds plus 3 nanoseconds and 3 nanoseconds. The total is 9 nanoseconds. In order to implement adders with a large number of ranks, it's usual the implementation interconnecting adders. We have to connect the carry out of each stage to the carry in of the next stage. The problem is that unfortunately the serial interconnection has the disadvantage of a low operation speed because it's necessary to wait for the carry out in every stage. An example. Well, imagine an example like this. This is the vector A, and this is, for example, the vector B. This is A0, A1, A2, A3, and imagine that we do the addition. 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1 again. We don't have in this case any carry out in any state. But imagine this other situation. This is the vector A and this is the vector B. 1 plus 1 is 0 for the S 0, and we have a carry out here 1. 1 plus 1 is 0, and now we have again a new carry out. 1 plus 1 is 0, and now we have again a carry out. 1 plus 1 is 0, and we have the last carry out, that is this one. Okay? As you can see, in this case, we need to propagate the carry out in each stage. This is the worst situation, when we have to propagate the carry out. Well, in this first case, we have the result, the vector S, that is this number, at 6 nanoseconds, because we obtain S0, S1, S2, and S3 at the same time. On the other hand, in this other case, we have to the first carry out, this one, in 9 nanoseconds, and a little bit more this one, and a little bit more this one, and consequently we obtain the vector S a little bit later. Okay, and now a question. How long does it take to have the definitive value in the output S1 and carry 1 when we have a 2-bit binary adders delay? Okay, think about it. Well, have you done? Okay, remember that we get the carry 0 at 9 nanoseconds, and we have to wait 9 nanoseconds plus 3 nanoseconds more to get the S1 at 12 nanoseconds. And we have to wait 15 nanoseconds to obtain the carry 1. Okay, congratulations. And now an activity. Get into groups of 4. Help each other. Well, a little bit more complicated. What's the 4-bit binary adders delay? Suppose that each gate is still 3 nanoseconds, the delay, and suppose the worst scenario, that is, carry propagation in every stage. You have to calculate the delay to get the last carry out, this one, and the bad news is that it isn't 9 multiplied by 4. When you get the last S3, you have the complete addition. Okay, good luck. Well, that's all for today. Thank you very much, and see you soon.